Hello, my name is Patricia Foley, and I'll be going over ICP-1 for cybersecurity. So for ICP-1, we have 4 different parts, and it was an introduction to PyTorch, specifically going over tensors, the conversion of tensors from a NumPy array over to a tensor and vice versa, along with how to build a neural network and how to load the data, both the training and testing data, and testing the network using different loss functions and optimizers. So let's begin. So the first step is to understand, understanding PyTorch is to understand that they use what is called tensors. And it's very similar to what an NumPy array is. You can have a one-dimensional tensor, or you can have a multi-dimensional tensor, whether or not it's 2D, 3D, and these graphics down here kind of represent that. So to begin, you'll need to import Torch along with import NumPy for part 1. So let's go ahead and run that guy. In addition, we're just going to build a very quick function, an activation function, and in this case it's going to be the sigmoid activation function that we'll later use when we're running our network. Next, we're going to create features. This can also be called data, and what we're going to do is we're just going to randomly generate normal variables for our data. In addition, we're going to initialize the weights and also the biases, a bias as well. And let's go ahead and show what the shapes are for for the weights, the features, and the biases. And so you can see this corresponds with what we initially specified, that we want a 1x5 array for the features, the same with the weights, and also the biases. Next, we're going to demonstrate why it's important to pay attention to the size, because if you just take this directly, multiplying the features and the weights together, you're actually going to end up getting this error right here saying that there's a mismatch in size. So if you go back to your algebra lessons, you have to make sure that if you have a 1x5 here, that means that you have to times by 5x1 instead of what we're doing currently. So to get rid of this error, we have to reshape weights, and then we can multiply the features and weights together, and then we can add those biases. Because what we're doing right now is we're just doing a very simple linear equation of y equals mx plus b. So we have the output is y, we have the features being x, and then weights is that m, and then plus b is the bias. And then after we get our output, we need to have that activation function, which we specified up above, which is the sigmoid function. So let's go ahead and do that, and the output is this tensor of 0.1595. Now that was a very simple linear equation, and overall networks, neural networks, that's what they are at each step. It just gets more complicated when you start adding different layers and different nodes together. So in this case, what we're going to do is very similar. We're going to set the seed, so that means that if we run this multiple times, we're still going to get the same output. We're going to generate random data here, along with we're going to have a hidden layer, we're going to have an output. We only want one, but in this case we're going to have two different layers. So we're going to have the initial weights, and then we're going to have the second weights along with the two different biases for each layer. So let's go ahead and run that guy. And then we're actually going to run this network. So we're going to do the first layer here where we're just, again, it's the simple linear equation of the features times by the weights and then adding the bias here. And then we're going to take this output and that becomes the data, and then multiply it by the weights and then the biases, and we'll get an output, which is the 0.3171. Lastly, we're going to demonstrate the conversion between NumPy arrays and tensors. So let's go ahead and just randomly generate a NumPy array. And this is A, so this is the NumPy array that was generated. Here we're actually going to take that NumPy array A and convert it over to a tensor, and that becomes B here. And then again, we're going to convert back to a NumPy array just simply by doing dot NumPy. And then just to demonstrate that both A and B are using the same memory locations, we're actually going to take this B and multiply it by 2. So it's just this guy multiplied by 2, we get this. And then just to demonstrate that A still equals B, even though you might think that they would be in different memory allocations, it's not the case. And so we actually have the matching the tensor and the original NumPy array still equal each other. Moving on to part 2, we're going to start using a different package that is provided by PyTorch, and it's the neural network library, and it's very easy to build a neural network using that particular library. So let's just go ahead right off the bat. Let's just get our some of the libraries imported. And the data set that we're going to use is the MNIST data set, and this is just an image of that data set, and it's just handwritten zeros, digits 0s through 9s. And we're going to continue on, and we're going to actually import this MNIST data set. And to do this, it's pretty easy. This right here is just normalizing the data, and this helps with, you want to normalize your data to help with outliers and things like that, and to help your network better performed. And so this is what, and this right here is just where we're actually loading that data. So make sure that we loaded that. So then the next step is we're just going to show what that data looks like. Just because we want to build the neural network, we need to know the different sizes of an image and how many images we're dealing with and the labels associated with it. And so as you can see, we have 64 images, and each of them are 28 by 28. And then the number of labels is 64, which makes sense. If we have 64 images, we need 64 labels. So let's go ahead and just show just one image here, and so we just happen to have the number 7. And let's keep going on, and we're going to use this activation function here. Again, it's a little different than the previous one, but this is the one we're going to use for this neural network. In addition, we're going to import the images, but in this case too, we have to flatten into a single array. So right now, prior to doing this, we had that 28 by 28 image, and now we're just going to have, which is a 28 by 28 matrix, and now we're just going to have a 1D array instead. In addition, we're just going to create some parameters. So we're going to have the weights and biases for the first layer, and then we're going to have weights and biases for the second layer. And this is where we're going to, this is the first hidden layer where we just take those images, our data, multiply by the weights, and then add the biases. And after we do that, we run that through that activation function that we specified up here, and we're going to take that H and run it through those outputs and run it through, multiply those guys by the next layer weights, add the biases, and we'll finally get our output. So let's go ahead and run that guy. And so what we're getting is, well, one, we wanted to see the shape. And so what it's showing is, so the output in our case, instead of, unlike the previous one where we had a single output, since we are trying to determine what that image is it a 1, is it a 3, is it a 7, we have to have 10 different outputs because we have 10 different labels. And so these outputs will eventually be the probability that that image is a 1 or a 9 or a 5. And then we went ahead and just printed those outputs there. So that's what this tensor is. So the next part is we're going to get into the probabilities. So right now this information it's great, but it doesn't really tell us what is the probability that this image is a particular digit. And so to do that, we need to have this probability here. And so in this case, we're going to use the softmax function, and all the probabilities have to add up to 1. And so let's go ahead and run this guy. And so again, the size is still going to be that 64 by 10. But in this case, and as you can see, this is just a quick demonstration that everything should equal to 1, and that's what it does. Next, we're actually going to use this library that I mentioned previously, where it's this neural network library. So let's go ahead and import that. And now we're actually getting into how you typically build a neural network in PyTorch. And so what we're going to do is we are going to start defining each hidden layer. And so in this case, we have one hidden layer and a single output. And we're going to define the activation function and also the softmax, which deals with the probabilities. So in this case, we have this hidden layer, and you specify this 784, and that comes from I believe the 28 times 28 should be 784. And after that, we have only 256 for the output, and that number has to be the same as the input for the next number or next layer. And then additionally, this specifies the number of outputs, and again, as I explained earlier, we have to have 10 outputs because we have 10 different labels. And again, these are the activation and softmax functions. And then in this case, we're just going to specify a feed for neural network. And so this means that it's just going to go from this hidden layer to through this activation function to this output, and then through this softmax to determine the probability. But again, this is a feed forward, so it's going to go this way. It's not going to go back. So now that we have that defined, let's go ahead and run that guy. And then next, let's actually set this this variable equal to our network that we defined earlier. And so as you can see, we have this hidden layer, which is linear. The in features are 784. The output features is 256, and so forth. So it matches what we specified earlier. Next is just to, what we want to do is, whenever you code, you want to have the simplest code possible and utilize the different libraries. And so there's actually this functional library part of the neural network library. And so what we want to do is we can actually simplify what our feed-forward network does. And so that's, let's go ahead and rebuild that network. And all you have to do, instead of actually specifying each layer as we did before, we can just simplify it by using f.sigmoid, self.hidden x, and very similar format for the softmax for the probabilities for the outputs. So let's go ahead and run that guy. And so that was just an explanation of that guy. Lastly, let's go back and actually redefine a different neural network, again using this functional library along with the overall neural network library. And in this case, we're going to have two different fully connected layers and then the output layer. Fully connected hidden layers is what I should specify, and then the output layer. So let's go ahead and run that guy. But again, as you can notice, we still have the 784 as the inputs and 10 as the output. And then we are specifying the feed forward network. So it's the fully connected layer 1 goes to this activation function. In this case, we're using the ReLU instead of, I believe previously we were using the sigmoid. Then we go to the fully connected layer again, and then ReLU again. This is your output, and then softmax is the probability. So we went ahead, defined that network, set it to that variable model, and again, this is what we ended up having. So the next step is to initialize the weights. And so to actually look at what the weights are for the network automatically initializes weights. And so you can actually customize them if you want to, but let's just go ahead and look at what they provided, or the network was initialized with. So to do that, it's just simply you have to call out the network you want to do, so that in our case it's model, and we just wanted to look at the fully connected layer 1 with these weights and biases. So if we wanted to do that for 2, we would just simply change this to 2 and so forth. Now in this case, we wanted to change the biases to just 0. So let's just go ahead and run that guy, and that's how you change it, is just you have this, and then you can do data fill, and you can do zeros if you want to do ones, so forth. And let's also do that, change the weights, but we want to normalize the weights with a standard deviation of 0.01. So let's just do a quick feed forward. And so we're going to take that training data that we loaded a while ago, and we're going to get the images and the labels, and then we need to resize this though, because if you remember, our first hidden layer has 784 as the input, so it can't be that 28 by 28 that we saw previously. And then after that, this is where we pass the images in, and then we'll just quickly show what the probability for each class is. And as you can see, this is actually what you should expect in this case, because our model isn't trained yet. So all we did was just strictly feed forward. The training comes is when you start optimizing the weights and you're using the gradient and doing the back propagation to actually train the model. So this is what is expected, that all the different probabilities should be basically the same. So next we're just going to run through, we're going to build a little bit different. We're just demonstrating what the sequential part of the neural network library is. So instead of actually specifying, previously when we had not only the network here but also the feed forward loop, you can simplify that even farther and just use this sequential part. So this is saying that we have this linear, we have an input size, which we specified here, hidden size of 0, but we had the ReLU after that. And then it goes hidden layer again, and then hit this hidden layer here with this particular size, and this is the output, goes into the ReLU activation function again. This is the overall output of the network before it goes into the probabilities. So this is, let's go ahead and run that guy. And in this case, we just again went through the feed forward as well, where we have the training data, we load the images and the labels, we reshaped them, and then we found the probability. In this case, it was 5, was the image that we were trying to find the probability of and classify. And again, you can see that it's just randomly assigning a class to this image. So in this case, let's just go ahead and look to see, this just kind of specifies like how you can actually look at a particular layer. So in this case, since we did not give any names to either the layer or the activation function, to actually look at this specific layer, you just do model brackets 0. And the same goes with if you want to look at the weights for that first fully connected layer, is just to use 0 instead of the FC1 that we used previously. So in addition, you can actually specify what the name is for each layer if you wanted to, and to do that you use this ordered dictionary. So let's go ahead and run that. And so again, just kind of demonstrating that you have the same, you're specifying the same thing, but you can actually call it out as FC1. So let's move on to part 3, and this we're actually going to get into the training of the actual neural network instead of having the network just randomly choose a class for us. So let's go ahead and again, same thing, import all of the libraries, and you specify how we want to normalize the data, and then on top of that, load that training data. Next, we're going to build our neural network. And so in this case, we're still using that sequential. We have 2 different hidden layers. We have the output, and then we have the ReLUs, or the activation functions. So let's go ahead and run that guy. In addition to that, though, we have a loss function. So this is, when you're training, you are wanting this to decrease as you're training. You don't necessarily want it to get to 0, because when you test it, most likely you're going to have an overfit model, but that is for a later time to discuss. Again, we're going to take the training data, we're going to load it, and we're going to do a forward pass, and then we're just going to quickly calculate what the loss was. And so what the loss is calculating is, you look at what the label is, and you look at what the model has classified it as. So you compare those two, and you end up with your particular loss. So next, we're going to build the network again, but we're going to do a slightly different loss. So this was a cross entropy loss, and this one it's just this particular loss, and we're going to see the difference in what the loss output is. And it's pretty similar. Again, though, it's because we have not trained our actual model. So let's go ahead and we are going to demonstrate. So gradients are what you look at for training, and so the gradients deal with backpropagation of a network. And so let's just quickly run through, and it's pretty easy in PyTorch to turn on the gradient. And so if all you have to do is just set this requires gradient to true, and you can see here that it did take that correctly. And so then the next thing is we're just going to show that because you have the gradient set to true, it shows what the gradient function is here. And so in this case, the function, since we are taking x to the power of 2 is equal to y, you have the power backpropagation function set. And then if you look here, this calls that specifically out. So if you wanted to know what that function was, you can just do y.gradient function, and there you go. Same with if you wanted to do the mean, it's the mean backpropagation, and also next, if you actually wanted to print out the gradient of this, you would just do x.grad, but in this case, we haven't calculated anything. We haven't done that backpropagation to calculate the gradients, and so that's why this is none as of right now. But let's just go ahead quickly and do like a backpropagation. And so as you can see, we actually do have gradients, a gradient now, because we did this backpropagation. So let's go ahead and combine all those together. So let's quickly build another neural network. We have a loss function, we have the training data, so let's just train the model really quickly, or run the images through this network. But then what we need to do is we need to actually train by using this backwards function here. So as you can see, previously we had a loss very close, or a little over 2, and now by just simply going back and training the model itself, the loss was significantly reduced to well under 0, or well under 1. Next is actually when you are training, you also want to have an you want to optimize the weights. So what the training changes the weights is what you're ultimately doing, is you're figuring out which weights needs to be associated with which nodes, and what that value of that weight should be. And in this case, we want to use an optimizer, and in particular, this is the optimizer that we are using. So let's go ahead and run that. And again, we're going to just take the training data. We have the optimizer. So the optimizer that we just set up here, but we initialize the gradients to be 0 since nothing has been trained yet, and then we train the network by using this guy, the backwards. So that's the output there. And finally, let's just look to see what the updated weights are. So that just kind of walked through how training is done, or the explanation behind the training. But that's typically not how you actually train a model in PyTorch. So let's actually run through how you actually train it. So you have this guy here. So you have the model, you have the loss, you have the optimizer, which helps with the weights. This is just the learning rate, which just means you can set a different learning rate for the weights, because if there's something called transfer learning, where you want to use a network that's already been trained, but maybe just retrain a few of the hidden layers. But in this case, that's not the case. So we're going to have 5 epochs. We're going to run through, and we, again, pull out the images. We have the labels, and you run through. Initially, set the gradients to 0. This is where you input the data into the model, but then you have this loss, but this is where the training actually occurs of the model, where you go back and refigure out the weights to get a better, smaller loss. So let's go ahead, and I did hit run, so this will take a little bit for that to run. Okay, so we're done, and as you can see, there's just 5 epochs, so that's what that specifies, and so we have 5 different losses printed out there. And overall, it looks like we did a pretty good job. The network is identifying or classifying the images correctly, with only a loss of 0.37. So let's just kind of look at one particular image. So this one looked at 9, and what you're doing is we're just looking at the probability right here, is calculating the probability, and as you can see, it has a very high probability that this is actually 9 and a very low probability that it's anything else. So this was correctly classified. So let's move on to the final part. And we're going to use a slightly different data set, and it's just this fashion MNIST data set. So it's just images of clothing. So let's go ahead, and we're going to do the full thing of not only training, but we're also going to have testing data. So let's load the libraries. We're going to set up, again, normalize the data, set up the training data and the testing data. Lastly, we're going to just show one particular image. This case, we're going to build the network really quickly. So in this case, we're going to have 2 different this is the input layer, this is the hidden layer, and this is the output layer. And we're going to use the softmax function for the probability, and we have the ReLU as the activation function. So let's go ahead and run that. This is going to be the loss function, along with this is going to be the optimization function for the weights, and we have a slightly different learning rate in this case. So let's go ahead and run that. And lastly, this is where the training actually occurs of the model. Originally I did have 200, but for this demonstration I'm just going to have 5 for the epochs. So the reason why we have the training and test data is you don't want your model to be overfit. So you don't want the model to only learn the training well enough that when you have random data that you are going to be gathering in the field or just in general, you don't want that data to be so different. The model is so well trained and overfit on the training data that it can't handle the real world data that it's going to have to identify. So it looks like we're done, and so our training loss was pretty good of just under 0.5. And let's go ahead and test our overall model by using this tester, and we're going to get the probability, and as you can see, it correctly classified our image of trousers, and the probability is very, very high that that's the case. So thank you for listening. That's the end of ICP 1.